Hello, welcome to Econometrics Melody. In this video, we'll discuss about the inverse Gaussian or the Wald distribution. Let us see some of the useful formula or the functions that are useful to calculate either the PDF or the CD of the inverse Gaussian distribution. Theta function normal, it will help us give the CDF for this value of the standard normal distribution, and 8.0, the standard normal distribution is symmetric. 50% of the area is covered towards the left and 50% of the area is covered towards the right. And for the score -1, the area covered less than -1, it is 15%, nearly 16% of the area it is covered towards the left, and towards the right we have 84.13% of the area. For this score -1, and for the score +1, let us see what is the CDF. Probability of getting 1 or less, it is 84.13%, while the greater than 1, it is 15.87%. Now let us see some of the useful formula of the inverse Gaussian distribution, and we'll calculate the PDF and CDF of this distribution. First of all, the mean. For the value of x, the mean is m, and for the value of m is our mean parameter, and for the value of 1 by x, the mean is 1 by m plus 1 by a, where a is the shape parameter, and its variance for the value of x, it is m cubed by a, where m is the mean and a is our shape parameter, and variance for 1 by x, it is 1 divided by ma plus 1 by a square. M is equals to mean and a is our shape parameter. Let us see the PDF. The formula for the PDF is square root of a divided by 2 pi x cube e to the power minus a x minus m, deviation from the mean, square divided by twice m square x. And the CDF of standard normal distribution, we can calculate it by using the CDF of normal distribution, standard normal distribution, for this value plus e to the power twice a divided by m and multiplied by the standard CDF of the standard normal distribution for this value. We'll calculate the CDF and PDF using these formulas also in our next section, and where standard normal distribution and its CDF of for x, it is calculated in its integral form by this formula, 1 divided by root 2 pi, and we integrate it from minus infinity to x e to the power minus t square divided by 2 and the change of t dt. Now let us calculate the CDF and PDF of the inverse Gaussian distribution. First of all, we take the parameter for the m to be 3 and its shape parameter 5, and for the value of x, I Gaussian, this is the theta function to calculate the CDF of inverse Gaussian distribution. And below we have it's a generic formula, normal, it calculates the CDF of standard normal distribution. For this value, let us say it's square root of 5, it is our a divided by x into x divided by m minus 1, and again e to the power twice a divided by m, and again the standard CDF of standard normal distribution for this value minus square root of a divided by x into x divided by m plus 1. And let us see, both of them should yield the same result, and the probability of getting 6 or less, it is 91%, nearly 91%. And this is I Gaussian CDF. This is the program written by Econometrics Melody to display the CDF of inverse Gaussian distribution for the parameter, mean parameter m to be 3 and the scale parameter 5. Let us see, probability of getting 6 or less. 6 or less, it is this value, somewhere between 86 and 93. And what was it? We had 86 and 93, it was 90. Now let us change our parameter mean to be 2 and our shape parameter to be 1, and for the value of x less than or equal to 9, what is the probability we are going to get by both the formulas? Let us say it is 96.9%, and let us check it in the CDF graph as well. 9 or less, 96, 9 or less, 96, somewhere over here. And we can also depict the graphical information of CDF of inverse Gaussian distribution for the parameter, any parameter m, and the shape parameter. So the CDF of inverse Gaussian distribution for mean 3 and the shape parameter a to be 12. Now let us calculate the PDF of the inverse Gaussian distribution. I Gaussian den, this is our theta function to calculate the PDF of inverse Gaussian distribution. for the parameter m, and this is our a, and x is 2.5, and this is our generic formula. Square root of it is a divided by 2 pi into x cube, and e to the power minus a m minus x square divided by twice, and it is m square into x, and both of them should yield the same result. So this will give us the probability of getting exactly 2.5. The value of x is 2.5, and by this probability we will construct the PDF, Gaussian PDF. It is the Econometrics Melody written program to calculate the PDF, to display the PDF of inverse Gaussian distribution for the parameter m to be 3 and the parameter a to be 5. And let us see, the probability is 22%. It's 2.5, it's 22, somewhere over here. And at the backdrop we have a normal distribution with the mean and the variance equal to the mean and variance of this inverse Gaussian distribution. Now let us repeat the same process, this time when the mean is equals to 6 and say parameter is 4 and the value of x is 5. So the probability of getting 5 by the theta function we get it is 7%, and by the generic formula it should yield the same result, 7%. And let us see it by the help of the graph. So for 5 we should get 7%, for 5 we should get 7%, and somewhere over here 7%. Similarly, let us draw the PDF, the graph for m to be 3 and the shape parameter a to be 12, and we should see this graph. Again, at the backdrop we have a normal distribution with the mean and variance equal to the mean and variance of this inverse Gaussian distribution. Now let us change the mean parameter and see what is the nature of the inverse Gaussian distribution. We are going to change the mean parameter all the way from 1 to 9, and we are for the shape parameter to be 12. Now let us reinforce this concept, and we are going to change the mean parameter from 12 to 24, and when the shape parameter is 30, let us see what kind of graph do we see. Now let us change the shape parameter, and we are going to keep our mean parameter m to be 12, and the shape parameter it changes from 15 to 25. And let us see what is the shape of the graph. Now let us repeat the process, and here m is equals to 35 while the shape parameter increases from 30 to 40. Now let us try to identify when do we get the inverse bell-shaped curve out of the inverse Gaussian distribution. For that we are going to change the shape parameter. We are going to increase the shape parameter in comparison to the mean parameter, and let us see, gradually we should get the bell-shaped curve. Now our mean is 12 and shape parameter is 120. Mean is 12, mean parameter is 12, and shape parameter is 120. And further, if we increase the shape parameter, we should approach towards the bell-shaped curve. Here the mean is 30 and our shape parameter is 1200. So the resulting inverse Gaussian distribution is to some extent like a bell-shaped curve. Now let us repeat the process. This time the mean is 9 and our shape parameter is 2700. We have increased the shape parameter significantly, and if we see it, it is ultimately a bell-shaped curve. So for lower mean parameter, if the shape parameter goes on increasing, it is ultimately a bell-shaped curve. Now let us see the area graph, the inverse Gaussian area graph. This is again the user written program. Econometrics Melody has written it, and this is useful for the hypothesis testing. For the mean parameter 3 and the shape parameter a to be 27, and the x is equals to 4.5. This is our null hypothesis, and we want to test the hypothesis that whether x is less than 4.5 or x is greater than 4.5. A single test, left tail test and right tail test. And by the very graph, it is evident that For less than 4.5, we fail to reject the null because it covers a major portion of the null region. And towards the right, also it covers 8% of the area, which is greater than our p-value. Actually, it is 8%, and which is again greater than the 5% alpha value. That is why in both of the cases, we fail to reject the null. So we conclude that the value of x is equals to 4.5. Now, if a certain process follows the inverse Gaussian distribution and we have a mean of 6 and a shape parameter is 50, now we want to test the hypothesis whether x is equals to 5. So we are going to perform a one tilt test, and let us see it by the help of the graph. For x is equals to 5, this is our null hypothesis, x is equals to 5, and the two alternative hypotheses, x is less than 5 and x is greater than 5. Again, both the region cover more than 5% of the area. So we fail to reject the null in either of the cases, either on the left tilt test or on the right tilt test. That is why we fail to reject the null, and we conclude that the value of x is equals to 5. Now let us, for the value of mean to be 2 and the shape parameter to be 2l, we want to test whether the value of x is equals to 4. Null hypothesis, x is equals to 4, and for x less than 4, it covers 97% of the area, and which is again greater than 5% alpha value. That is why we fail to reject the null in this case. And for x is greater than 4, we cover only 2%, nearly 3% of the area, which is less than our 5% alpha value. That is why in this case we reject the null, and we conclude that x is in fact greater than 4. The last example, where the mean parameter is 3 and our shape parameter is equals to 90, and we want to test whether the value of x is equals to 2. X is equals to 2 is our null hypothesis, and we have two alternative hypotheses, either x is less than 2 or x is greater than 2. Depending on the situation, we perform only one alternative test, either left tilt test or the right tilt test. So for x is greater than 2, it covers 98% of the area, which is greater than the 5% alpha value. That is why we fail to reject the null. And for x is less than 2, it covers only 2% of the area, which is again less than our 5% alpha value, and we reject the null in this case. And in this case, we conclude that the value of x is in fact less than 2. For this right tilt test, we conclude that the value of x is equals to 2 because we failed to reject the null. Now let us see some of the uses of inverse Gaussian distribution. I have collected it from different sources. Inverse Gaussian distribution, actually it is used in various fields like finance, engineering, and physics. Inverse Gaussian distribution is used in modeling the time between arrivals in a Poisson process. Inverse Gaussian distribution, it is used in modeling the duration of a telephone call in a call center. These are some of the examples. In inverse Gaussian distribution, it is used in modeling the distance between two genetic markers on a chromosome. It is used in modeling the lifetime of mechanical or electrical devices. Inverse Gaussian distribution, it is used in modeling the time until a default in credit risk analysis. It is used in modeling the arrival times of customers in a queuing system. It is used in modeling the time of failure in reliability analysis. It is used in modeling the time of diffusion in a diffusion process. Inverse Gaussian distribution is used in finance as a model for the underlying asset price in the Black-Scholes option pricing model. And there are many other uses of inverse Gaussian distribution. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.